Okay, so I want to apologize in advance for the way these notes are going to go. I do not own a printer at home, and since it's a snow day today, I don't have the resources to print one at school. So what I'm going to be doing is probably what you should do as well, is I'm going to be taking notes, and I'm going to kind of talk as I'm writing, but I am also going to have to look over at the notes which are displayed on my computer over here to my left. So if there are any pauses, it's because I'm looking at my notes to make sure that I have the right example and saying the right things. So what might be nice for you right now is if you pause this video and go to Google Classroom and open up a copy of the notes so that you can see what I'm talking about as I'm writing it down. So I'll try to stay true to the notes as much as possible, but again, forgive me for not printing ahead of time. So what 2.2 is about the inverse of a matrix. So you remember from 2.1 and from other things that we actually can't divide a matrix by another matrix, but I can find the inverse of a matrix. And the inverse of a matrix is much like a multiplicative inverse from algebra. So, for example, the inverse of 7 is 1/7. And if I multiply 7 times 1/7, I get 1. And that's exactly the same thing we're going to do with matrix inverses. So we call the inverse of a matrix, let's say we have a matrix A, we call the inverse A, and it looks like to the negative first power. If I multiply those two things together, and A inverse is the inverse of A, I should get the identity matrix. Remember, which is the matrix that has ones along the diagonal. Okay. You can call it anything else you would like, but this is the most common notation for A inverse. One fun fact is that if A is invertible, this inverse is unique. And there's a proof on the notes that we're going to walk through here. There are going to be a couple of proofs in this chapter, and you're going to want to be up on kind of some of the techniques for proving. So my proof is going to be by contradiction. And the idea, if you do a proof by contradiction, is to say that the thing we want to be true, A inverse, is unique, a unique inverse. Let's say that's what we would like to be true. Let's say it's not true. Okay, so B and C are inverses of A. Okay, we are going to try to do rigorous mathematical things, algebra, with B and C then, and then get to some place where I get a contradiction, where something I write down is not true. And then, because that's something I wrote down is not true, and because I did rigorous algebra or some other kind of mathematical process to get there, then it must lead all the way back to say this statement that I first wrote down is actually the one that's not true. And then, if this is not true, then B or C must be unique inverses of A. So let's just start with matrix B. Okay, I can write a matrix as that matrix times its identity. Okay, that makes sense. Multiplying B times the identity matrix is still going to give me B. But since I know that C is an inverse of A, and I know that multiplying a matrix by its inverse is going to be the identity matrix, I can say that this is actually B times CA. Okay, that's me just saying if C is an inverse of A, multiplying them together will give me the identity. But, okay, one other property about inverses is I can multiply them in the opposite order. Okay, multiplying C by A will give me the identity, and multiplying A by C will also give me the identity. Okay, so both of these things are true. This is the one time that matrix multiplication is commutative, and it's commutative because they both give me the identity matrix. Okay, but I know from 2.1 that matrix multiplication is associative. Okay, so I could reassociate B and A. Since B is also an inverse of A, this means that this is I, the identity matrix, times C. But the identity matrix times C is just C. So B equals C. Okay? Okay, this contradicts that C and B are, what's the word I'm looking for? Independent, I guess. I don't think that's the word I'm looking for. Independent inverses of A. Therefore, A has a unique inverse. QED. Okay. Alright, so in conclusion, okay, the inverse of A, a matrix, times its inverse, is equal to the inverse times that matrix. Either way, they're both equal to the identity matrix. And I added this little n in here to show you that the identity matrix could be for any dimension. Okay. An important follow-up, though, is that not every matrix is invertible. Okay. If it is not invertible, we call that a singular matrix. Okay. If it is invertible, we call that a non-singular matrix. Okay, and now we're going to talk about how can we find the inverse. Okay, so there are a couple ways we could do it. Some that are a little bit more simple than others, some that will require a little bit of a proof. So let's say example 1, we are given this matrix A, which is -3, -4, 1, 1. And we would like to find A inverse. Okay. One way we can tackle this is to make a system of equations. We know that A times A inverse is the identity matrix. Great. Which means -3 and, oops, not negative, 1, -4, 1, times, let's call this just A, B, C, D, okay, is equal to the identity matrix 2 by 2. 0, 1. Goodness. Okay. Well, I can get a system of equations from this. Okay, just by multiplying the two matrices together. So, multiplying the first column in the first row will give me -3A minus 4C. And that should be equal to the first component, 1. If I multiply the first row in the second, or excuse me, the first column in the second row, I should get A plus C equals 0. So that will tell me A equals -C. And if I sub that in here, I'll get 3C minus 4C equals 1. So -C equals 1, C equals -1. That tells me A equals 1. Okay. All right. Then we want to deal with the other components. So I deal with the second row. -3B minus 4D should be equal to 0, because that will be this first entry. And B plus D equals 1. So B equals -D. Okay. Oops. We should get, oh, wait a second. I didn't do that quite right. I was looking at A and C. So B is 1 minus D. There we go. That's better. Okay. So if I plug that back in, I'll get -3 plus 3D minus 4D equals 0. Okay, so I should get that D, okay, if I add this up, I get -1D. So D equals, oh, sorry, my computer is having a ball over here. Okay, this is what I get for trying to do math in my head on a snow day. Gotta come up here. Okay, so -3 minus D equals 0. So negative 3 equals D. Okay, that means B equals 4. And finally, I guess maybe we'll write this on the next page. No, you know what, we're going to write it here. Sorry, filled notes later. Okay, A inverse is 1, negative 1, 4, negative 3. Okay, how could we check that? We could multiply A by A inverse and see if we get the identity matrix. That would be how to check that. Okay. So let's keep going. There is another way to find the inverse. Okay, and this one I am not going to prove. I'm going to hope that you will use the same method we just did, okay, with the system of equations to try to prove it yourself. The Theorem 4 says that if A is a 2 by 2 matrix, yay, I got an email, CD, okay, and that A times D minus B times C does not equal 0, which, if you remember from multivariable calculus, that is the determinant of this matrix. Okay, then A is invertible, and the inverse, okay, and let's read a little funky formula, is 1 over the determinant of A, so a constant, some kind of constant, times D negative C negative B A. Okay, and you're like, what the actual heck is that? Okay, one way to remember it would be to switch A and D, and then negate, or if you want to call multiply by negative 1, B and C. Okay, so we switched A and D, made B and C negative, or switched their signs depending on what was already there. Okay, whatever helps you think about that. Okay, so the proof is that we would like to figure out how we got this formula. Okay, so the idea given in the notes is that if A is A, B, C, D, and A inverse, okay, assuming that it exists, is x1, x2, sorry, I need to go in order, x4, if I multiply those two things together, okay, times A, negative 1, should be the identity matrix. Okay, so again, just like we did in the last example, multiply these two together and go component by component, okay, to try to get some kind of system of equations for this. You will get something super, super weird. It's like if you multiplied this into each of these components, and that's okay. That's what you're looking for. Okay, but I'm going to leave that proof for you guys to do. I might also link a website that has it in the notes. Okay, one key thing though, so like an if and only if kind of thing. Okay, the matrix A is invertible if and only if the determinant of A does not equal 0. And if you think about that, if we were finding this matrix A, we wanted to find the inverse, we couldn't divide by 0. So this inverse would not exist if our determinant of A was equal to 0. Okay, so let's do one example of this. Okay, so example 2 says that I have the matrix 8, 5, 6, 4, and I would like to find the inverse. So the first thing I should do is find the determinant. So the determinant of A, because if I don't find the determinant first and I do all this weird switching, what was the point? Okay, because I want the determinant to be non-zero. So the determinant would be 8 times 4 minus 6 times 5. Okay, 8 times 4 is 32. 6 times 5 is 30, so I get 2, which is non-zero. A, in fact, is invertible. So A inverse will be equal to 1 over the determinant of A times switch A and D, so 4, 8, make the other two negative. Negative 5, negative 6. Okay, so A inverse, if I distribute that 1/2 in, is 2, negative 3, negative 5 halves, 4. Okay, and how could you check that? Which I recommend, multiply them back together. Okay, multiply this matrix times this matrix and make sure that you get the identity matrix. Okay. Another theorem here. Okay, if A is an invertible matrix, let me just write this down. Yeah. Okay, so where I am is I'm looking at theorem 5. If A, invertible, and n by n, okay, and for all B in Rn, okay, the equation AX equals B has a unique solution. And that solution is X equals A inverse times B. Okay, so short proof. Let's see how this works. Okay, so if I have AX equals B, okay, I can multiply both sides by A inverse. As long as I do it to one side, okay, I can do it to the other. But A inverse times A is the identity matrix. And identity times a vector is just that vector. So the answer, quick short proof, is that that X value must be equal to A inverse times B. Okay, but is this unique? Sidebar. Okay, so let's let some other vector, u equal x. Okay, I want to prove that this is still our only solution. So if I assume that u is a solution, and au equals b, I go through the same process, multiplying each side by the inverse of a. Okay, well, u equals A inverse B. I get the same thing. Okay, so there is a unique solution, regardless of whether or not I said it was this one or if it was some other thing. Okay, this is our only way to get there. Our only solution is by multiplying B by the inverse of A. One note about the preconditions, though. Okay, A has to be invertible. Okay. 2 has to be squared. Okay. All right, so let's see how we can apply this to what we've been doing in chapter 1. So if I have the system, okay, 8x1 plus 6x2 equals 2, and 5x1 plus 4x2 equals -1, okay. Remember that this is our system of equations. So I would have the matrix A be 8, 5, 6, 4. Okay, then I have the vector X be x1, x2, and B is 2, -1. Okay, so what we've been doing is row reducing, which is totally fine. Okay, but what we're going to do now to find X, let me write that down. X is x1, x2. What we're going to do now is we're going to use our inverse properties to figure out what that X should be. Okay, because the proof we just did says if I multiply this vector by the inverse of this, I should get this answer. Okay, well, let's make sure A is invertible. Well, good thing A is the same matrix we just did in the prior example. Okay, so if you look back at the other page, A inverse is 2, -5/2, -3, 4. And I want to multiply that by this vector. So let me say that A inverse times B is this times this, and this should be equal to the x we're looking for. Okay, 2 by 2 component, or excuse me, 2 by 1, so I will get 4 plus 4, and -5 minus 4. Where did I get 4? I think I added. What in the heck? So 4 plus 3, there we go. So my answer, my solution, my unique solution to this system, okay, will be 7, -9. Now, this is what's going to come up in 2.3. I've just said that if A is invertible, then for every B in that Rn, the equation has a unique solution. So you need to think back and think, when are the other cases in which a system of equations would have a unique solution? Okay, so just think about that as we're going forward. Okay, all right, theorem 6. Wow, we're only halfway there, guys. This is a long lesson. Maybe I'll break it up into 2 parts. All right, theorem 6 says several things. Okay, if A is invertible, then so is A inverse. And the inverse of A inverse has to be A. Okay, so that's the first thing. Second thing, okay, and this kind of feels like the transpose that we talked about last lesson. A and B, n by n invertible matrices. AB is then also invertible, and the inverse of A times B is the multiplication of their inverses in the reverse order, which is exactly the way the transpose works. Okay, and then last one, if A is invertible, then A transpose is invertible. And, as I was saying, the inverse of the transpose matrix is the transpose of the inverse matrix. Ta-da! Okay. All right, so I'm going to go ahead and pause here. There are a couple more examples in the notes that you're going to want to do. I'm going to go ahead and do them so you can check your work, but I'm not going to spend any more time going through them together, just to save you a little bit of time of watching. All right, but that's it for, I'm going to say 2.2 part 1 about matrix inverses. I'm going to do another video on elementary matrices in a minute.